Right, I also had to modify, I wasn't real happy with this problem set, so I made some modifications. I sent those out earlier today. Right. So the first one is 3.4.1. We have a bar that's terminated on a rigid termination here. So this, the left end of the bar doesn't move. And it's free to move on the right end. And all we want to do here is look at the normal modes, the standing wave modes here, the first three. And you know that the longitudinal motion of the bar here satisfies the wave equation. So it's just like waves on a transverse waves on a string. It's just that it's longitudinal here. So we know what this is going to look like. The lowest, or what we call the fundamental mode, will have to look like this. It's fixed here and it comes in at zero slope here, because the bar, there can't be any force on the end of the bar here because it's massless, and there's no medium here that it's pushing on. So the displacement has to be flatter. There can't be any rate of change of displacement, because otherwise there would be a strain. So this looks just like transverse modes in a string, except here we're plotting the longitudinal displacement, quarter wavelength. So it just moves up and down at some frequency, and we get the frequency by noting that there's the wavelength is 4 times the length of the bar here. You can see this is a quarter wavelength, as I mentioned before. So then we use the fact that the frequency is the speed of waves divided by the wavelength to get the frequency. Here's the next mode up. The next mode up will have one interior node. We usually use the word interior to make sure there's no confusion, because there is a node here at the end, right? So when people are describing modes, to be careful, they'll usually classify them by so many interior nodes. So this has one interior node. And you can see that there's 1, 2, 3/4 of a wavelength here in the length L. So from that we get the frequency. And it's not twice, these aren't harmonics here. We're missing the even harmonics, as we discussed. That's due to the mixed boundary conditions here. The same thing's going to happen in acoustics for sound in a pipe. And that's why I launched off into the organ pipe thing. Remember, blocking the end of it? Kind of counterintuitive, right? If you have an organ pipe, why would you block the end of it? Well, you could save yourself a lot of length if it's a very deep bass note. Lower the frequency by a factor of 2. And finally, the third one here, again, odd harmonics. 2 interior nodes. What's the frequency of the fundamental? Well, here it is. It's a quarter wavelength. Now, I just noticed before class that really the natural way to do this is in the some of you are, you're starting to use this appendix, right? Have you used this? Okay, you're going to use it a lot. I keep telling you that. But don't worry, it'll happen. Maybe, and I guess this is where it starts. Maybe this is where it starts. So you'll notice here it's got a lot of tabulations of quantities, and you can look up whatever material this is. I don't know what material this is. Steel? Okay. You can look up the speed of sound in steel, speed of longitudinal waves in a steel bar. And it's presumed there that the wavelength is large compared to the diameter, so it's Young's modulus. You actually don't have to substitute in what C is. It's the square root of the Young's modulus divided by the density. You can just look this up. It's easier to do that. But however you want to do it, I did it the long way here. You get about 2.52 kilohertz. So again, as you go on in the sequence, you'll find this appendix is really useful. There's 3 tables in there for solids, liquids, and gases, different properties, including speeds of sound. Okay, so we're going to stop this. This problem here. We'll get into this kind of stuff in other problems. Right? Is there any questions about this? By the way, there's the 4th and final lab is this week, right? Modes of a bar, yeah, the famous modes of a bar experiment. Now I just noticed I didn't catch this earlier. This should be a capital S, so please replace that. I didn't bring my chalk thing. So we typically use A for amplitude. We don't want to use it for cross-sectional area. We use capital S, which can be confused with lowercase s, right? Stiffness. So in a case like that, you always dress this up. That's what I do. And I should have done it here. You can just do something there. That'll work. Remember, I think we talked about this. If you want to make it clear between these two, you just put something like that. These things have names because in the 1800s they had a lot of time and they gave names to all this stuff. I don't know what they are. I don't care. Okay, but you know, you want to always pay attention to notation, right? Because we have so much of it. Okay, so this is 5.1. Steel bar, we're given the cross-sectional area, the lengths. It's free to move at x equals 0, and it's loaded with a mass here. And I don't think they say it, but we're going to assume that this is, we can treat this like a point mass. Remember I talked to you about that? You could have waves in there. So we're going to treat it as a point mass. So there's the information that we have. Compute the fundamental frequency of longitudinal. This is free mass loaded. We, I've forgotten now. There are a number of possibilities. We did this both for a string and for a bar, or we did it for a string and not for a bar. I'm pretty sure we did do it at least for a string. But if we didn't, then we could have done it for a bar. I don't know. We did this either for a string or a bar or both. Maybe that's the best way to say it. And here's what you end up with. Here's the transcendental equation that you end up with. In terms of the mass on the end and the mass of the bar, or the mass of the string, in the case of transverse waves, same equation. The modes here correspond to intersections. This is a general technique when you want to solve, f of x equals g of x. You plot the two functions, the function of x, and where they intersect are going to be the solutions. And we have this nice dimensionless ratio of the masses. That's what's relevant. What's the mass of the bar? It's the cross-sectional area. It's the volume of the bar times the mass per unit volume, which we call the density, right? So this is going to give you the mass of the bar, and it's equal to this. Oh, I've gone to the appendix to look up the density of steel. Incidentally, some of these, you want to be aware of this. There are different types of steel, okay? And even probably more important, I think there are many types of aluminum. So you can get different, these values, these aren't written in, this is not written in stone here, okay? This can vary depending upon the material. So if you ever get involved and you have to be precise about this, that's why we have the National Institute of Standards, right? NIST. That's part of their job, or I think so. It should be. So you can get some information directly from them. I don't think you can get everything. They want to charge you. Has anyone ever had to do this before? You might have to do it for your theses. I've had to do it for research before. But there's a lot of information out there on the internet, right? And some of it's contradictory. But anyway, if you do get into this problem of having to know parameters precisely, be prepared. You can find contradictions, and it can be difficult. What you want to do is just stay away from that, hopefully not have to deal with very precise values. All right, so this is the mass of the bar, the density of steel times the volume of the bar. The important thing is this dimensionless ratio here. Now look at what's significant about this. This could be anything, right? It could be very large, it could be very small. It can't be negative. But what is this very roughly? It's on the order of what? Unity, 1. This means we can't can't make any approximations. We can't assume that this is going to be approximately a free end or approximately a fixed end. When this is of order unity, we can't make our, remember we talked about this, how you we've talked about it several times, you can make approximations here when this ratio is either close to 0 or very large. And you get, this will be either behave as a simple case of a free or a fixed boundary. So here you're stuck, you know, you're not going to get, the root's not going to be close to pi or the first one here is not going to be close to pi or pi over 2. These correspond to the simple boundary conditions. We're going to be roughly in between, right? So here's the equation we have to solve. Here it is. X is in radians here, right? This X is in radians. And so this, you've done this before, I think. We did it in a problem set, right? Probably the last problem set. I can't remember. But and if you think you're not going to use this on the next quiz, you're way wrong. Okay, so you're going to get a chance to do this. It's actually fun. I think it's fun. So here it is to, and if anybody disagrees, let me know. I got it to 3 figures here, and you usually stop here. So you just do it. It's just sort of trial and error. And I mapped out how I do it anyway. I actually make a table and just start zeroing in, you know, narrowing it down. And you can see here that it's got to be between pi over 2 and pi. So you start somewhere roughly in between here. If you don't, you can end up at another root. So anyway, I find 2.12, this is for this dimensionless number, what I called x here, which is really KL, the fundamental KL. So from that, once we know K, we know the wavelength, we can get the frequency. And here I looked up the speed of sound in aluminum, I think. We can find the frequency. And this is what I get. Yeah, so I'm sorry, this should be capital S, right? Make sure everyone, that should be capital S. Okay, there's more. What problem are we doing again? 5.1? Okay. Yeah. So, this is good. Determine the position at which the bar may be clamped to cause the least interference with the fundamental mode of vibration. Okay, well we need to, I jumped right into this in the solution here, but we need to look a little bit more physically. I put it over here. So this is going to have a fundamental mode. Right, what does that look like? Well, if we're a fixed end, we would have a free bar. And what does the fundamental mode of a free bar look like? There's a node right in the middle. That's the demo, right? Remember the, oh no, that's, yeah, this one, right. The rosin. So there's one interior node, right, symmetrically located. What happens to that node when I start to mass load this? Well, let's go to, the best thing to do is just go to the extreme. What if I put an infinite amount of mass here? The node will be over here. So, because we're in between, roughly midway, you know, because of our, in some sense, you know, we're roughly midway between free and fixed. We expect the node to be somewhere right around here. So let's calculate that. How do we calculate that? Well, I know that I have a solution of the wave equation here with a free end. And I know it's a standing wave. So I can immediately go to this. It's going to be some amplitude times the cosine of K1x. This is for the the 1 signifies the fundamental. Why do I have a cosine here? Because it has 0 slope at the origin, right? It's free there. And I have separate an e to the I omega t times the spatial dependence. This is a standing wave solution to the wave equation that respects the First, the boundary condition on the left. Now, I'm trying to encourage you, I've been for several weeks now, to just write this down. If you still feel uncomfortable, write down an arbitrary right traveling wave, add it to an arbitrary left traveling wave, impose the boundary condition, the simpler one, impose this boundary condition, and you're going to get something that's equivalent to this. Okay, is that clear? Eventually you're going to get tired of that and you'll just start writing this down. So, all right. So a node here means that this quantity is pi over 2. And we're after x. Well, we know x will be given by this. We know k1. Well, we know k1L. It's easier just here. That's because that's what we solved for numerically. The whatever it was, 2.12. So I'm going to multiply numerator and denominator by L to get my nice dimensionless quantity here and plug the numbers in, and I get 0.185 meters. Now, is that reasonable? What's the length of the bar? It's a quarter of a meter. So this is an eighth of a meter, halfway. So it should be between 0.125 and 0.25, and is it? Yeah, so that's reasonable. Reasonable result. You always want to do these checks because sometimes you can be way off, right? And if you're way off, you probably made a mistake. Okay. Oh, finally, this is interesting. We're asked what the ratio in part C here. In the fundamental mode, what is the ratio of the displacement amplitude of the free end to the mass loaded end? Well, we know this is going to be less. Right? When you mass load this, the node moves over here, and so the waveform is going to look like this. It's going to have less amplitude, but precisely what is it? Well, we can get that simply. We don't care about time, or we just care about amplitude. I'm going to add a 0 on here to refer, A is the amplitude at x equals 0, because the cosine of 0 is 1. So just to emphasize that, I'm going to put a 0 here for this part of the problem here. Oh, good, and I wrote that in. Okay. So the ratio of the amplitude will be, the amplitude at x equals L is just going to be the cosine of k1L, the absolute value of that, times A0. So the ratio of these two amplitudes has to be this, and we know k1L, we solve for that, it's approximately cosine of 2.12, and we get 2, roughly 2, 1.9 something. So that's how much the amplitude, I think we're asked for this. A0 is going to be, this should be greater than, has to be greater than 1, and we get that it's about 2, which is reasonable. And again, it's especially reasonable. It's not a very large number. It's not close to 1, and it's not a very large number. Right? And why is that? Because they designed this problem to be intermediate between the two extreme cases, roughly intermediate. They clearly designed it. They wanted something on the order of unity. Okay, any questions about that one or comments? Okay, 5.2. So there was a change here. I didn't like, I think we should stay away from part C. So this is a new change. We're killing part C, right? And then we added, coincidentally, a part C for a later problem, which that's good. I think those are good changes. Okay, so 5.2, yeah, this is interesting. So here we have a mass connected to a wire. And of course, we're in a gravitational field here. So that's the purpose of this, is to deal with this. So it's a 2 kilogram mass hanging on a steel wire. We're given the cross-sectional area, we're given the length, And you know that this is going to have a bar is similar to a spring, right? So this is going to have we'll have some longitudinal vibrational frequency here. So there are different ways that this can be solved. We want to find that frequency, I guess. Yeah. Okay. So one way to look at it is that this wire has a small mass compared to the mass here. So neglecting its mass, we can think of it as it's going to have a spring constant. Okay, and the spring constant here corresponds to uniform expansion and contraction. Why don't I get waves on here? In general, we've been solving problems, right? Where you get waves. What is the wavelength here? It's very big. The wavelength is going to be very big. Because we have, the lighter this is compared to this, the longer the speed of waves is very big, relatively big here. So we're going to get approximately uniform expansion and contraction when this thing oscillates. And in that case, the displacement here, remember, c is the displacement. When it's uniform compression and extension, this is the strain here, the dimensionless strain. I can just evaluate it. It's the change in total length divided by the total length. It's just delta L over L. When I take something and statically, this is, for a very light mass here, we're in the quasi-static limit. It's like we're slowly, because the speed of sound is speed of waves is so great here. It's like we're in the quasi-static limit. So I'm going to get this uniform extension. And this is our formula. Remember, this is what basic formula for the force of one part of the bar and the other. I'm going to evaluate it by looking at the end down here. And I get this expression. And you can see that we can beat this into Hooke's law. Well, it's very easy. We don't have to beat. We just recognize that these numbers right here combine to give the spring constant, little s. Now, this is a quick way of deriving something we talked a lot more about in lectures. So you can look back and remember we had that special topic in the lecture notes. Because this comes up a fair amount. Dealing with the spring, thinking of a bar as a spring, so it has a spring constant. And it comes up in cases where you have approximate uniform compression and expansion. Because that's how an ideal spring behaves, right? An ideal spring, and by an ideal spring I don't just mean it solves Hooke's law, that it obeys Hooke's law, but I mean that we don't worry about waves on there. Right? We assume the spring is so light that any time it stretches or compresses, it's uniform. So really the assumption we're making there is the speed of longitudinal waves in the bar is fast compared to what we're doing in our experiment here, or the problem we're working on. Well, once you know this is now chapter 1, right? Incidentally, gravitational field is not important here, doesn't occur. So this is the frequency of a mass on a spring. We know the spring constant. We know the mass, right? So we can just plug the numbers in here. Again, looking up at the appendix, I went to the Young's modulus, and we get this frequency. Okay, so that's part A. Any questions about part A? So now we're going to do in part B, this is interesting, is we're going to do a better job here. Although not perfect, and I'll explain that. I shouldn't, but I'm going to explain that in a minute. We're now going to do this calculation again, but we're going to think of this as a fixed mass-loaded bar. And we have an exact way of approaching that. Well, exact once you get to the Transcendental Equation, and then we make approximations, right, in the solution of the Transcendental Equation. Okay? Now, why isn't that exact? This is kind of hard to see. It seems like it's exact, right? But let me give you a hint. What we're doing is we're taking this and we're looking at it like this, right? there really is, in here there is a gravitational field. What effect is that going to have? Is the tension going to be constant along here? No. So when we take this thing and rotate it 90 degrees, in equilibrium, there's going to be, in string language, there's going to be a uniform tension here. In bar language, there's not going to be any, it's just going to be uniform, right? There's no strain. In equilibrium, there's no strain. But the effect of gravity here is not just to stretch this. The stretching by itself, I don't think it changes, it doesn't have any effect on the frequency. But it's going to be a non-uniform strain here, because this little segment here has to support this weight, right? And it's the weight of not just the mass, but the weight of the wire, which is a small effect, but still, we said exact, right? We're talking about exact solution here. And as you go higher and higher up, you have to support more and more mass. So the strain, it'll be straining more in equilibrium. Yeah. So this is, we got non-uniform strain here. This is a little bit of a problem here. But it can be solved. I've solved it before. Okay, but anyway, let's look at our model here where we're taking this in our usual case, right? Making it horizontal. In that case, we get this. We've been through this in strings and or bars. The appropriate transcendental equation now looks like this. All right. And now we compute our dimensionless ratio, the mass on the end compared to the mass of the bar. And we get 26. That's large, pretty large compared to unity. What do we mean by large compared to, I don't know, we're going to find out. That's really, I think, part of the point of this problem here. So we now are solving this. And you know that an approximate solution is going to be just making this infinity. So that would be, in that case, it would be we'd be looking at the fundamental mode of a fixed bar, right? The mass is very heavy on the end. But we're going to do it exactly in the context of this model and use the 26 rather than infinity. And again, so you get to go through this again, right? You're going to become experts on this calculator approach to solving these transcendental equations here. And I get this to 3 figures. So that's our KL number. From that we can get the frequency. And I get this. Okay? And you can see it's pretty close. In fact, the way we look at this, when you want to know how close, don't tell an acoustician or a scientist, any kind of scientist, that what's the difference between these? Let me put it to you this. What's the difference between these two? Anybody?
5%. No, nothing.
Nothing? Okay. Look, the way we do this is, it's almost always we look at the percent difference. That's the relevant thing. That's what you find. And that's what you're supposed to be beginning to find in the lab. Maybe it's slow to happen, but it'll eventually happen, okay? What's it really, almost always when we don't really care about the frequency, the absolute frequency difference here. We want to look at the difference divided by the average, and we just want a rough value. So the way we often do it is, and here's the way how I came up with this, you can see that this is 0.78910. It's 4 parts out of about 1600. 4 parts of the difference here, this minus this, is about 4 parts out of 1600, which is 1 part out of 400, which is 1/4%. And that's fine. We don't need this very precisely. We just want to get an idea. So typically, when you're on the fraction of a percent level, that's typically pretty small. And all kinds, if you really need to get down to that kind of precision, you're going to be dealing with probably all kinds of other errors that are coming in. You got trouble. You're going to have trouble. Usually we don't want to look too close when you're doing an experiment, right? Because it's realistic. There's going to be all kinds of effects. But sometimes you have to. All right, so where were we? Oh, yeah. So this is reasonable. Oh, is it, let's ask some other questions here. This is less than that. Is that reasonable? Yeah, because we're including the mass of the bar. In fact, something that this is embarrassing, I just thought of right before class is, what happens if we've got the spring constant, right? What happens if we add 1/3 the mass of the bar to this and find the frequency? Remember that? That should work. Now this is more accurate than that, but at this level, because this mass is so small compared to this, we're talking about a small effect here. The 1/3 the mass of the spring might work pretty well here. I didn't get a chance to do it, but I'm going to do it. It looks like I got a space where I can write it in here, where something else was in the past. Okay, so I think is there more to this problem? No, we're going to omit the rest of that. Okay, any questions or comments on that problem? Okay, the next one is 6.1. We have, they say here, a thin bar. What does that mean? What does that mean?
And compared to wavelength. Does that mean the wavelength's much longer than
yes. That's what they mean when they say that. And if you're not initiated in this stuff, you might have no idea what that means. You know, thin compared to what? Okay. This is practical. This is a practical problem. In fact, since I have to edit these anyway, we can add the word sonar here. Okay, so as I mentioned to you before, bars are used in sonar for projectors, for sound transmitters. And suppose you're not happy with the frequency and you want to lower it, and you've got a bar that's involved here. You can mass load it, right? So how much mass do you put on there? Do you just start playing around? Ooh, you can, but you're going to quickly find, especially if you're doing this is underwater, you got to have an underwater tank or something. It can be a lot of trouble. So you want to utilize the theory, and we can handle this theoretically. So here we are again. We've got a mass-loaded bar. So we're starting off with, the reason I dashed this is we're starting off with just a fixed free bar. And the problem is we want to lower the frequency by 25%. Okay, so we want the frequency, resonance frequency here, to be 3/4 of what it is. We want to add a mass and have the resonant frequency be 3/4 of what it is without the mass there. So the general problem here with the mass is, again, it's this, what we've seen many times before for strings and bars. And I think I briefly mentioned this, but maybe I should mention it again. You know, you can equivalently, this could be the tangent of KL, and then what would you have over here? 1 over it, okay? So there you would be dealing with the intersection of the tangent curves, not the cotangent, but you don't have a straight line, okay? So conceptually, you know, you can have it, this would be 1 over KL, which looks like this, right? So this came up on just the past quiz that was graded. So conceptually it's fine, but computationally it's easier to deal with a straight line. So that's why we go with this. But you don't have to. This could be a tangent, and this will be 1 over that. Okay, so the unloaded solution corresponds to just pi over 2. K over L being pi over 2. And now we want to add mass, this little m here, which brings this slope of this line up here a certain amount, such that This value is 3/4 of this value. Now, wait a minute. We want to get the frequency, the new frequency being 3/4 of the original frequency. Why am I going to KL? Well, KL, the frequency is proportional to KL. You can see that here. You know, K is 2 pi over the wavelength, or however you want to look at it. Skip the step here. And C is equal to the wavelength times the frequency. So you can see here that KL is proportional to the frequency. So what we want to deal with here is KL. That's our natural dimensionless quantity here. So to get a frequency, to drop the frequency by 25%, I want to drop KL by 21%. So my desired KL value is going to be 75%, 3/4, of the solution of the free bar, pi over 2. So this is the key step here. And then one of the reasons I like this problem is you start off thinking, oh, I'm going to have to do this solution again, this calculator solution, right? This looks like we're going to have to solve a transcendental equation, but you don't. We just want to find KL such that it's 75% of pi over 2. So we just substitute that into here and solve. We just punch in very little here. We don't have to use trial and error. We just determine the mass ratio. And there's the value. That's the value. So this is the mass you need to add to the end here is going to be 0.345 times the mass of the bar to give you that lowering of the resonance frequency by 25%. Okay, any questions? And again, that's it's interesting, and it is practical. Okay, so the next problem is 364. Determine the expression giving the fundamental frequency of longitudinal variations of a fixed free bar of length LMS if the reacts. Okay, so it's not that free, is it? So here's how we would draw it. Okay, they're giving us a reactive terminating impedance here, which is a spring-like. You notice the impedance is like an inductor. So this is the problem we want to do here. We want to look at longitudinal vibrations here. And we want to find the fundamental frequency, right, in general. Actually, and we're not given values, so this is going to get down to a transcendental equation. You can't take it any farther without knowing the values. Okay, I corrected it there. This is the cross-sectional area. So why does the displacement look like this? Well, it's free, right? So we have to have no slope, and omega is equal to ck. We have. But again, if you're not happy with this, write down the right and the left traveling and pose this boundary condition. You're going to find this. Now, what's the boundary condition at x equals L? Well, you can write down Newton's second law. The force on this face of the bar here, the net force has to be 0, because otherwise we'd have an infinite acceleration. And this is undergoing simple harmonic motion. This is steady state. So we have to have 0 force. Well, you can do that, but the quicker way is to just use, we derived this in lecture, the quicker way is to use this. This works for any terminating impedance, and we get it from it's equivalent to Newton's second law. So if you know the impedance, which we do here, it's just a stiff, I made a mistake. Oh, maybe I didn't say it. This is not an inductor. It looks like an inductor, but it's a spring. It's equivalent to a capacitor electrically. I might have said, okay. So the impedance of an electrical capacitor is 1 over I omega C, right? Where C is the capacitance. And there's an inverse relationship, unfortunately, between the stiffness and the capacitance. We're going to eventually get rid of that down the sequence. We'll be talking about the compliance of this rather than the stiffness. And the compliance is 1 over the stiffness. So there, and compliance starts with a C. Why is that advantageous? Because the equivalent electrical thing is a capacitor, and the capacitance measured by capacitance C. So what we're going to be doing, this makes it a lot easier. And I know you think I'm crazy, but anyway, when we write down this is the impedance of a capacitor, this is just going to correspond to the mechanical case where we have to do this. This is the mechanical compliance. So it makes it a lot easier. So that'll come about in the transducers course, 44, 54. I think I mentioned this, maybe I didn't, I can't remember, but it doesn't matter. Anyway, you might want to look back. This is basically that the terminating impedance is the complex force divided by the complex velocity. You can see this is proportional to the force, the rate of change of strain, remember? And this, of course, is the velocity. So that's what this is. It's what it's equivalent to. So we plug in our form here, and the amplitude, we don't need, the amplitude is irrelevant. This is all linear, it scales. The amplitude, there's going to be an A there, it falls out. So we end up with our transcendental equation here. That would be the next step, then be to solve this. And we want to put it in nice form. You can see here that I've used, we're again using, you should suspect that this is going to naturally emerge. Because we have a spring constant here, in order to know what a large value and a small value means, we have to compare it to something else. And the only other thing around is the stiffness of the bar, which is given by this, like we talked about in lecture, right? And sure enough, when you do this, you see that all that's important is the ratio. So here are the cotangent branches. Here's the linear branch, and the fundamental will be right there. Now you can it's interesting to take this problem a step further. I'm not going to do that, but it's written down here. And if you're interested, you can check it out. One of the interesting things here is that in a typical case, if this is a real bar, and this is a real helical spring, what's going to be the relationship between the stiffnesses? What do you think? What do you feel? This is going to be huge. Yeah, huge. Probably at least in the thousands. I don't know, but it's going to be typically very big. Because, springs are made that way. Helical springs are made that way, so they'll be soft compared to a bar. It's part of the idea there. So, in that case, in the more practical case here, what's this system going to behave like? The answer is chapter 1. Like we were talking about before. It's a mass. This is going to be essentially rigid. Or this spring just can't do anything. We're not going to have waves on there. For the fundamental mode. For the fundamental mode, right here, it's going to be, so it should reduce, and you can check that. It's going to reduce when the stiffness of the bar, when this quantity is when this is essentially infinite here, okay? So this is going to be up here. So we're going to get a solution. Now you say, oh, it's going to go to 0. Well, yeah, but you don't want to go all the way to 0. You've gone too far. On a scale like this with motion, longitudinal waves in here, it is close to 0. With this thing just going back and forth like a rigid mass. That's relatively very low frequency. But you can get the result out. And the result has to be that the frequency is the square root of the stiffness divided by the mass of the bar. So you eventually get it out. Well, you can check this, and if you have any questions that you can ask me. There's another case that's, oh wait, I'm sorry. This is a different limiting case. This is going the other extreme. Right? The practical case here is when the stiffness of the bar is much greater than the stiffness of the spring. And eventually omega squared is equal to, we get it. That's what we'd have to get this. It takes a little bit of work to dig it out of the math though. Right? Because the math is all based on the rod undergoing vibrations. And sometimes these limiting cases, they have to be in there because our theory will cover that. But sometimes it takes effort to get it out, especially up here. Look at this. This is the other limiting case. I had to go through a lot of effort to get the result out there. So you can look at that if you're interested, and you can always let me know if you have any questions or comments. Okay, so the last problem is 737. We're going to add part C. You'll see why. So here we again have now it's a long, thin bar of length L, and now the reason I assigned this, I still remember this, years ago. We got to so far we haven't done any forcing, have we? These have all been like normal mode type problems. So we want to do a forcing problem. So here we have this applied force on the end. We're going to take a free end. So now, I got to have a solution of the wave equation here. It's going to be a standing wave, right? In a steady state, it'll be a standing wave. And because this is a free end, I've got to have 0. The derivative of c with respect to x has to be 0 here. So I know that this has to be the form of the standing wave. It's got to be a standing wave, so I got my e to the I omega t separate from the x dependence here. It'll have some amplitude that'll be uniquely specified by that force, and the drive force and the drive frequency. And you can see that at x equals L, I get the cosine that's going to come in flat. So this obeys the free boundary condition here. Again, if you have trouble seeing this, write down the right blah blah blah. Right? The right traveling, the left traveling. Impose the boundary condition. You'll find that you get this. With a little bit of effort, you get this. So now I want to look at the origin. And here we could use impedance, but the point of this is actually, I think the point here is sort of to derive the impedance. So we're going to look at, as an exercise, so we're going to look at Newton's second law. What does Newton's second law tell us about this end of there can be no net force on that, as we've discussed before. So here's that statement, the net force is 0. We have an instantaneous external force given by this. The force on the bar is, because we're looking at the right on the left, going from right to left, we got to change the sign here. This happens in a string too. And you may recognize this is our sort of fundamental expression for the force. It's very similar to a mass on a spring. You can just replace this c with a y. And to make it even more explicit, the connection with a string, and to make it easier on ourselves, we almost always replace this sy, the cross-sectional area, times the Young's modulus with rho L c squared. So I'm going to do that. And now when we do this, this forces the amplitude. The amplitude has to be given by this. Well, this coefficient, right? And you got to, there's a sign change here. That means there's a 180-degree phase difference. So to be precise, we keep that. So this is what we find for A. And that goes right in here. We now have the displacement. Here it is. This is the displacement for any point along the bar, in the steady state for this drive. And now we can recognize the amplitude of the standing wave. All of this stuff right here, and we don't care about the minus sign, right, for amplitude. This right here, the combination of all this will be the amplitude, the maximum amplitude. And we get this. The next part here is to form the input impedance as the complex force. We're just given this, but we've found the response. We've found everything we really need to know here. I mean, there's more that can be done in this problem, but we've done most of it by finding this displacement here, by finding this quantity. So to get the velocity, I need to get the complex. I'm going to take the time derivative of this. That's easy. It just brings down an I omega. And the I omega t's canceled. The f naughts cancel. This is all linear. And does that look familiar? Yeah, it's the same as a fixed free string. When you drive, this is the input impedance. And in fact, it's a special case of the impedance translation formula. If you look back, maybe some of you can see it in your head, but if you look back, what's our terminating impedance here? 0. Okay? So you just go to the impedance translation formula, which works for it gives you the impedance seen here for any terminating impedance with a medium, a wave medium in between. And now you just set the terminating impedance equal to 0, and you'll see that you get this. That's a general way of looking at this from the impedance translation formula. Any questions so far? One final thing here, and this is what, don't tell anybody that I said that if you have a bar here and a bar here of the same material but a different area, that there are no reflections. Please don't tell anybody I said that. It's embarrassing. I was way off. And one of the things that got me way off was the wave impedance. So this is going to take just a short time, very short, believe me. Let's now imagine that this is infinite. And I want to know, what's the input impedance? Do I just let L go to infinity here? You can see that's going to be trouble, right? Because as L goes on, this just keeps oscillating between 0 and infinity. The branches of the tangent function just continue. So what's the mistake? How do we get out of this problem here? What's the assumption in here? Way back here, how did we get this? Well, I've been encouraging you to write it down, but where it comes from is you have a right traveling wave and a left traveling wave. If we want to solve the infinite, semi-infinite bar case, we assume there's no left traveling wave. So you got to go back to the beginning. We did this for a string. You got to go back to the beginning and just have a right traveling wave. And then look at Newton's second law on the end. Go through what we did before, and what you're going to find is the impedance, the input impedance, that is the impedance seen by the drive for this case where there are no waves coming back. It's purely resistive. That energy goes, it never comes back. So it's very different than when you have it terminated. And it's rho LC. The mistake I made was thinking it was rho C. This is the mass per unit length of the bar. Okay? Any quick questions or comments? All right, tomorrow we start this flexural motion.